The next thing we want to look at in part 3 of our lecture on chapter 9 is on power production. We've already seen how turning a crank that rotates a coil of wire in a magnetic field can generate electricity. That's the principle of a generator. Specifically, in this case, we have an alternating current generator. Now, the way it's typically done is you have steam that's directed through a turbine, and as it passes through the turbine, it causes the turbine to rotate, just like wind would rotate a windmill. And how do we generate this steam? Well, we need heat, and different places do it differently. So you might have a power plant that burns oil or natural gas or coal. You might have a nuclear reactor that's generating heat. But basically, all of these kinds of power plants, they generate heat to boil water and make steam. And that steam is directed in such a way that it turns a turbine. That's just like in the previous part of the lecture, we talked about the person turning the crank to rotate the coil. Well, the steam passing through this turbine here is going to rotate it and cause this coil to rotate inside this magnetic field, and that's going to generate electricity. Now, on a large scale, that is going to go to your house, to your office, to the shopping mall, everywhere that power gets delivered. And by the way, the steam's not the only way. For example, I mentioned a windmill. Windmills can be used to generate electricity, and they work the same way. The wind turns the turbine, rotates the coil, etc., etc. A waterfall can work the same way. You dam up a river so the water level rises, and you let the water fall through the holes in the dam, and as they do, they pass over a turbine, and they rotate the turbine and generate electricity. But most of these situations where you have power generated this way, it involves some physical action that's turning a crank, or in this case, turning a turbine, which rotates a coil in a magnetic field, which generates electricity. Now, one of the interesting things about alternating current compared to direct current is that with alternating current, you can use a transformer. And a transformer is a method of changing the voltage of something. So, here we have a picture showing the basic configuration of a transformer. You have a bunch of coils. Now notice these coils are separated from each other. You have what's called the primary coil and the secondary coil. And you have current that flows in the primary coil, and there's basically two things going on here. The current in the primary coil, what do currents make? We know that currents make magnetic fields. And if it's an alternating current, it's going to be a changing magnetic field. Now, it turns out that if you have changing magnetic fields passing through loops, that generates currents. And so you have the coil over here. The current, the original current, is generating a magnetic field that's changing. That magnetic field is passing through the second unconnected set of loops, and that generates a new current in the second loops. And so you can transfer the current from one coil to the next coil by this process. Now, here's the cool thing. By changing the number of loops of one coil to the next coil, you can vary the voltage in the current. You can make the voltage go way up, or you can make the current go up. But whatever happens to one, the other will get the opposite. So here's why. Remember, what's generating our electricity? We have something that's turning a crank or turning a turbine. It might be someone's hand turning a crank. It might be the wind turning a windmill. But we have something that is doing work. It's applying a force to something and causing it to rotate and turn. And that work is happening, so many joules of work are going into that system every second, and that's creating power. Now, if you remember, in an electrical system, power is equal to the current I times the voltage V. Now, power depends on how much work the crank is putting into the generator every second. The energy per time, that the work being done per time, that's the power. And that's fixed by conservation of energy. But what this transformer can do is it can ramp up the voltage. But if the power is fixed by conservation of energy, if the voltage goes way up, the current must go down. On the other hand, if you make the current go way down, if you make the voltage go way down, the current will go way up. So one goes up, the other goes down. And that's accomplished by this transformer. Now, here is the basic relationship of a transformer, and you can see a more modern version of the transformer. In the previous slide we had, you could see the loops. It was more of a picture to kind of get the idea across. But here's what an actual transformer might look like. And so this region right here is the primary coil, and this region down here is the secondary coil. And the relationship is this. The voltage that comes out of the secondary coil divided by the number of loops in the second coil is equal to the voltage that's input into the primary coil divided by the number of turns in the primary coil. So this term over here, the voltage in the primary coil divided by the number of turns or the number of loops in the primary coil, that's going to be some number. Now let's look at the voltage that comes out of the transformer. That's the voltage of the secondary coil. If I change the number of loops in the secondary coil, it's going to change the voltage. That's how we can make the voltage go up or go down, by changing the number of loops. Now let's look at an example where we can use this equation to do some quick calculations. So part A of the example says a 120 volt DC signal is input into the primary coil of a transformer with 15 loops in the primary coil. If there are 60 loops in the secondary coil, what is the voltage output of the transformer, i.e. the voltage coming out of the secondary coil? And the answer is, it's a trick question. The answer is 0 volts. Why? Because this only works if you have alternating current. If you have DC, which stands for direct current, a transformer just won't work. It's got to be AC. And I just noticed that in my part B, I had DC listed there as well, and I just changed it to AC. So the part B was supposed to read, a 120 volt AC signal is input into the primary coil of a transformer with 15 loops in the primary coil. If there are 60 loops in the secondary coil, what is the voltage output? So let's look at our formula over here. We want to know what the voltage of the secondary coil is. So if I multiply both of these guys by N sub S, I can cancel this guy and solve for Vs, and I get Vs is equal to N sub S over N sub P times the voltage of the primary. So now I can just do a little bit of arithmetic here. So my Vs is going to be, the number in the secondary coil is 60, divided by the number in the primary coil, which is 15, and then that's going to be times the voltage in the primary coil, which was given to be 120 volts. And so 60 divided by 15 is 4, and so the voltage output from the secondary is 4 times 120, or 480 volts. Now, I've put 120 volts AC into my transformer, and I get 480 out. So my voltage has been stepped up to a higher voltage. Now, remember, the cost of this is that my current gets weaker. And so that's the reason that you can do this. You're not violating any kind of conservation law, because yes, the voltage is going up, but that's not coming from nothing. It's coming at the expense of the current, which is lowered. And by the way, if you reverse the transformer so that the secondary coil becomes the primary coil and vice versa, then the ratio here, 60 over 15, would be 15 over 60. And then you'd be multiplying this guy by 15 over 60 instead of 60 over 15. And the voltage would get lower. And so this is the thing about a transformer. If you use it in one direction, the voltage gets higher, but if you change the input to the other side, then the voltage will get lower. And so transformers can be used to step voltages up very high or then step them back down to lower, more reasonable voltages. Now, why would you want to do this in the first place? Why would you want to use transformers? Because it turns out the bigger the current is, the more that a wire will heat up. And so imagine that you have a power plant and you're generating power over at the power plant, and you want to send the power down the power lines to somebody's house or business or whatever, and so you want to send it down these long transmission lines. Well, here's the way that you do it. You generate the power at the power plant, and then you use a transformer to ramp the voltage up very, very high so the current is very low. The current will travel down these long wires for miles and miles and miles, and then there'll be a transformer near your house that reverses the direction so that the voltage gets cranked back down. Now, over the long miles and miles of cable where the current is very low and the voltage is very high, there's not much heat of the wire, and so you're not wasting energy heating up the wire. I don't know about you, but I would not want to pay in my power bill the cost of making the wires to my house hotter. And so the power company is doing us a solid by ramping these voltages up so that we don't have to spend a lot more money paying for energy that we're not even using. Now, we have already talked about Faraday's law in terms of current loops and magnets being pushed into loops. I want to talk about Faraday's law from a different context now, a broader context, one that you don't even have to have a wire for. And so this is the broader, more real version of Faraday's law. And what Faraday's law tells us is that changing magnetic fields create electric fields. So if I plunge a coil down a loop of a wire, I'm changing the magnetic field seen by that loop, and that's going to create an electric field down that wire. If the wire is a conductor, guess what's going to happen when you put an electric field on a conductor? Charges will flow. Yes, that's what we've talked about previously. And so the changing magnetic fields create electric fields, and if there are electrical wires, you can get currents traveling down those electrical wires. But even without the wire, you'll still have the electric fields, because remember, electric fields can exist even in the vacuum of space. Now, Faraday's the one that discovered this, and another guy named Maxwell, James Clerk Maxwell, he discovered that the reverse is true. If you have changing electric fields, that can create magnetic fields. And Maxwell made one of the most important discoveries in human history. For thousands of years of human existence, people looked up at the sun and the moon, they looked at fire, they saw things that were creating light, and they wanted to know, what the heck is that stuff? What is light? And Maxwell figured it out. He was the first human in the history of the human race to really understand what light was. And so here was Maxwell's basic idea. Imagine you have a charged particle and you shake it back and forth. As you shake it back and forth, over here, the electric field generated by that charged particle is changing because you're either getting a little bit closer or a little bit further away. So the strength of the electric field over here is changing. Now, here's the rule. Changing electric fields make magnetic fields. And so this changing electric field caused by vibrating a charge back and forth is going to make a magnetic field. Now that magnetic field didn't exist before, so you've got no magnetic field, suddenly you're creating magnetic fields. That means that by definition, you have changing magnetic fields. Changing magnetic fields create, guess what? Electric fields. New electric fields are going to be generated by those changing magnetic fields. And guess what those electric fields are going to create? You probably guessed it, they're going to make new magnetic fields, which are going to make new electric fields, which are going to make new magnetic fields, and so on. Now, Maxwell was able to figure out that what would happen is that if you took a charge and you vibrated it back and forth, it would create a wave of electric and magnetic fields that were coupled together, and that wave would travel out into space. And he was actually able to come up with some equations that showed how that wave would work, and he was able to use it to calculate the speed of that wave. And when he found his answer, he probably fell off his chair or came near to it, because it was the speed of light. Maxwell was the first person to understand that light was an electromagnetic wave created by vibrating charges. And so here you can see a depiction of an electromagnetic wave. And again, it's in 3 dimensions, which is kind of hard to draw on a 2-dimensional surface. But if the direction of the wave is going this way, really, you're looking at a screen that's sending electromagnetic waves, sending light to your eyes. And so think of it not as going over here diagonally down, but coming out of the page. And so you're going to have some of the electric fields are going to be going up and down. The magnetic fields are going to be going left and right. They're all perpendicular to one another. That's what this guy is trying to show. And so you've got the wave is traveling this way. The blue part represents the magnetic field vectors that are traveling perpendicular to the direction of the motion. And then you have the electric field vectors in pink that are also perpendicular to both the direction of the wave and the magnetic field. If that's confusing, don't worry about the directions. I don't care if you understand it or not. It's not that important for this level of a class. But what I do want you to understand is this idea of how light is generated by vibrating charges, because that is just really, really cool.